lecture 9, topics covered. So we have successfully learned the first topic. The first topic is on gradient. Gradient, in which we have learned that if we are given the potential value, we can find the E field by using the E field equals to negative gradient of V. So this is the equation for the gradient, which enable us to calculate the electric field intensity value if we are given the potential value at any position or any point. Right, and we did examples on this potential gradient concept. So now we are going to proceed with the second topic of lecture 9, which will be the last topic, the last topic for chapter 4, in which we're going to have a look at this energy density, energy density in electrostatic field. So objective for our lecture today is on the second objective here, which is to calculate the energy density of a charge structure. Okay, so which means that if you are given any charge structure, for instance, if you are given a line charge, which is having a rho L density in coulombs per meter. So we want to calculate what is the amount of energy density produced by this particular charge structure.
Energy, doctor, not charge.
Come again?
Calculate the energy density of charge.
Yes, correct. Yes, correct.
Okay.
Yeah. Right. For instance, if you have a a structure like this, a structure which consists of a cable, a cable. For instance, if we have a cable which made up of conductors, for instance, this is conductor, and we have a charge of rho s, for instance, and outside here is a negative rho s charge. So you want to calculate what is the amount of energy confined or produced by this particular charge structure. The amount of energy produced by this particular charge structure. So this is what we're going to learn in our lecture today. Calculation of energy density or energy if you are given a charge structure, any charge structure. So you should be able to calculate this energy. Right. So hopefully you have some ideas on what we're going to discuss today. Okay, so let's have a look at our discussion for this week. So this is what we have learned last Thursday. So, right. Okay, this is the one, Okay, so as I mentioned just now, if you are given the charge structure, for instance, if you base on this slide, we have a structure of charge, line charge of rho L. We have a structure of a surface charge, and we have a structure of rho V charge, volume charge density. So the question is, what is the amount of energy conserved or confined by this particular charge distribution? Okay, so that's our concern. We have to calculate the energy, the energy that is confined or that is conserved by this particular charge distributions. So to discuss about this energy, or to formulate the equation for this produced energy or confined energy or conserved energy, this is the development of this formulation of the equations. So we're going to start with this particular case, in which if we have a system, a system whereby we are having 4-point charges. Okay, so we always start with a very basic charge distribution, in which in this particular case we are having 4 point charges, which are labeled as Q1, Q2, Q3, and Q4. Okay, so basically we want to calculate, so based on what we have understand earlier, we are going to calculate, or we're going to obtain what is the amount of energy. What is the amount of energy that is said to present, or that is said to be conserved by this particular system of charges, which contain of 4-point charges. Okay, so basically you're going to start with these 4-point charges, and afterwards, based on the obtained equations or obtained formulations, we are going to expand it, or going to extend it into other cases. For instance, line charge, surface charge, or volume charge. So we are going to start with a very basic charge distribution. So 4-point charges. So in order for us to find the energy that is present in this particular system of charges, basically is equals to find out what is the work done in positioning or in producing or in locating these particular charges. Okay, right. So basically, in order for us to find the energy conserved in the charge structure, we need to find the work done in producing this particular charge. Okay, so this is what we're going to learn now. We're going to produce, we're going to calculate what should be the amount of work. Okay, so for instance, in order for us to find the work done by the external source in positioning the charges, okay, so the first step that we can do is that we are assuming that initially in this particular system, there is no charge. Yeah, there is no charge. So basically, we just have the system is empty. Yeah, the system is empty. So afterwards, the second step is to bring the charge of Q1. Yeah, the charge of Q1 from infinite position into the system. Yeah, into the system. So basically, yeah, if we base on definition of work that we have learned in lecture 8 previously, if we can write here, we have the work is equals to Q negative Q integrations of E dot dl. Yeah, this is the equations of work. Okay, in which if we can recall back, basically if I have a external field, electric field external, and if we have a position of B, yeah, this is repeating what we have learned previously, B to A, we are trying to move a charge of Q from the point of B to the point of A. Yeah, so a movement from a point of B to the point of A, in this particular case, will then produce a work in which it is given by negative integration of Q, integration of from B to A of E dot dl. Okay, so in this particular case, if we consider the same situation, initially we have considered that there is no charge inside. Yeah, there's no charge inside. So in this particular case, we can see that there is no electric field, in which electric field equals to 0, right? Electric field equals to 0 because there is no electric field which is trying to prevent the charge to move. Yeah. So in this particular case, the point of B should be at infinite. Yeah, it should be at infinite because we are saying that the charge is brought. Yeah, it's brought from the infinite position and to the point of A, which is this point here. Yeah, it's the point here, is the point of A. Hello?
Yes, doctor, to the point of A inside the system.
Correct. Is it okay if you can switch off your mic then?
Oh, sorry, doctor.
Okay, thank you very much. Yeah. Okay, so basically E will be 0. Yeah, due to this phenomenon I mentioned just now, because there is no E field that will act on this movement of charge of Q. So as such, the E will be 0, and following that, the work will be 0. So that's why we have mentioned here that there is no work required in moving the charge of Q1 from infinite to this position. Okay, right. So that should be the second step. We have position, or we have locate the Q1 inside the system. Okay, so the third step is now we are trying to bring in the charge of Q2 to this particular system. Okay, so now from the equations of work equals to Q, integration of Q of E dot dl. Okay, so we can say that the Q will be the Q2, yeah, because we bring in the charge of Q2 from outside, and the E basically will be due to this charge of Q1. Yeah, so in which if I can re-sketch the problem just now, so let's say this is a point of infinite, the point of A, for instance. So we try to bring in the charge of Q2 to the point of A, okay, in which there is the E field, in which this E field basically is produced by the charge of Q1. Yeah, charge of Q1. So due to this, we can write that this particular E field is due to charge of Q1, and as such, we're going to have these particular equations, yeah, in which the W2, the W2 basically is this particular case. Yeah, the charge of Q2 should be there, and this E dot dl basically will be the potential. Yeah, potential at the point of Q2 due to the charge of Q1. Yeah, I repeat again. The E dot dl basically will be the potential. Yeah, because we have learned this previously. E dot dl integration with potential, in which this potential basically is potential at charge of Q2 due to the charge of Q1. And the total work up to now will be a summation of W1. What is W1? W1 is a work needed in positioning the charge of Q1, in which we have learned previously that it will be 0. And W2 is the current work or present work, which is Q2 of V21. And that should be our equation of work 2, yeah, given by these equations, yeah, right? If you can have a look, I mean, based on what we have learned previously, the E dot dl infinite to, let's say, the R. So we have learned that E will be Q over 4 pi epsilon naught of R squared, direction of R, and dl will be dr of R dot product. So we're going to have integrations of Q over 4 pi epsilon naught of R dr from infinite to R. So that we're going to have Q over 4 pi epsilon naught of R, yeah, infinite to the point of R, and we're going to have Q over 4 pi epsilon naught of R. So R is a distance, yeah, R is a distance from Q2 to Q1, which is given by R21 here. Okay, so that should be our total work up to third step, which is we have now positioned two charges, Q1 and Q2, into our system. Okay, okay, so this process will be repeated for step 4, which is to bring in the charge of charge of Q3 inside the system. So now the charge of Q3 has been positioned, and if you base on this diagram, your work 3, yeah, work 3 basically will be, work 3 basically will be need to be considered. Yeah, we need to consider potential at Q3 due to Q1, and also potential at Q3 due to Q2. Okay, so as such, if you base on this, you are going to have the work of W should be given by this equation. Okay, this is total work so far. Yeah? So total work so far, total work will be W1, W2, W3. W1 is to position the Q1, W2 is to position the Q2, W3 is to position the Q3. Okay, why we have these two terms here? So I mentioned just now, this is Q1, this is Q2, this is your Q3 just now. So we are going to have potential of Q3 due to Q1. So this is a V31, and we have also potential at Q3 due to Q2. This will be potential of V32. Okay, so as such, it can be written now to be equals to this equation, and the second terms should be written as this equation. Yeah. Okay, so hopefully you understand this phenomena of the equations that describe the total work up to this level. Yeah. Okay, so that should be the total work so far and up to positioning the charge of Q3. Yeah. And finally, we're going to position the charge of Q4 into the system. And if we look carefully based on this particular case, we are going to say that the potential, the work done in positioning the charge of Q4 will be considered the potential due to 3 charges. Yeah, potential at Q4 due to Q3, potential at Q4 due to Q1, potential at Q4 due to Q2. Okay, so if we can write here, we're going to have W4, yeah, W4 only, yeah, will be Q4, in which potential at 4 due to charge of Q1, plus potential at Q4 due to Q2, plus potential at Q4 due to charge of Q3, plus potential at Q4, sorry, yeah, Yeah, potential at Q4 due to charge of, sorry, I think up to now, up to this level only, sorry for that. Okay, so we have this work value, work value at charge of Q4, in which if we can have a look at the equation for that, yeah, this is our Q4, yeah, this is W4 that I mentioned just now. So we have three terms there, yeah, this is the work due to Q1, work due to Q2, and work due to Q3. Okay, so this is the work, total work required to bring in all the four charges into the system. Okay, yeah? And basically, we can also have a case whereby the subscription can be interchanged, yeah, in which we can say that if we base on this equation, yeah, so this equation, we can write that this is equals to Q2 of V21, and also it can be interchanged to be equals to Q1 of V12. The same things happen to this. You can also have Q1 due to V13, and we can also interchange this to be Q2 due to V23. So the subscript for this can be interchanged. So we are going to find out the average value for this, in which the average value for this work can be then returned to be these equations. Okay, so we have come out with this average work, total work, yeah, total average work, in which we can say that if we base on this equation, this is the V12 plus V13 plus V14, in which we can also write this as a V1 only, yeah, because if we base on this V12, it means that this is potential, yeah, this is potential at charge of Q1 due to charge of Q3. This is potential at charge Q1 due to the charge, sorry, V12 is potential at charge Q1 due to charge of Q2. V13 is a potential at charge of Q1 due to charge of Q3. V14 is a potential at charge Q1 due to charge of Q4. So in general, we can just put that this will be the total potential that will be incurred on charge of Q1, and we can write just as a V1 only, which is potential at Q1 charge. So the same thing is applied for this equation, in which we can just put this as a V2, which is potential at charge of Q2, and the same thing is applied for this, which will be returned as potential at charge of Q3, and this as potential at charge of Q4, yeah, or total potential at charge of Q4. Okay, so that will be the general equations that we have obtained finally for the case of total work that we required to develop or to locate these 4-point charges. So based on this, yeah, we can simply write the equation as mentioned here that I mentioned just now. The total work for that particular 4-point charges will be written as half of Q1V1 plus Q2V2 plus Q3V3 plus Q4V4, in which it is mentioned here that this is V1 is potential at charge, or yeah, charge of potential at Q1. V2 is potential potential at Q2, and the same things will follow for V3 and V4, which is potential at Q3 and potential at Q4. Okay, so the work basically can be calculated, yeah, by simply multiply the charge amount Q1 with the potential, yeah, at that particular charge. Then we then sum them up together, and that should be our work that we required, yeah, or that should be the energy conserved in that particular charge structure. Okay, so this idea shall be then extended, yeah, shall be then extended, in which we're going to extend this into a case of continuous charge distribution, yeah, in which, as what we have learned previously, this is for the case of discrete point charges. So for the case of continuous charge distribution, a summation will be modified to be an integration. Half should be there. Q is returned to be a dq, and V should be now returned to be, Vk is now returned to be the V only, in which the dq will be depending on your charge structure. For instance, if your charge is a line charge, So it should be half V of rho L dl. Yeah, that should be your dq. If your charge is a rho s, so your dq is a rho s ds. And if your charge is a volume charge, so your dq shall be written as rho v dv. Okay, so from this definition just now that we have learned that this particular Vk is basically the potential at that particular charge. So the same thing is applied here, in which the V, yeah, this particular V basically should be the potential at your charge structure. Yeah, potential at your charge structure. Okay, yeah, so that's why I mentioned here that V is the potential at the charge itself. Okay, so this is the equation that can be used to calculate the energy conserved in your charge structure. Okay, energy conserved in your charge structure. So if you are given, for instance, yeah, if you are given a charge, a line charge, for instance, yeah, so we have, let's say we take that the charge is having infinite in length, yeah, the length is infinite. You are given that the density is rho L coulombs per meter. So in order for us to find the work or the energy conserved in this particular charge structure, yeah, so you can use this equation, which is integrations of half V rho L dl, in which in this particular case, you only need to find out what should be the potential of V. So potential of V is potential, yeah, V is potential on the line charge. Yeah, potential on the line charge. So that should be your equation that can be used to calculate the work or the energy of your charge distribution or charge structure. Okay. Alternatively, there is another equation which can also be used to calculate the energy, in which the equation basically is given by this integrations of half d dot E multiplied with dV, in which we can prove that this is basically obtained from the previous equation, for instance, half integrations of dq of V. So basically we can write that the half d dot E dV is obtained from these equations that we have formulated in the previous slides. Yeah, but I'm not going to prove how this equation is produced. Yeah, so the proving I left it to you to look on your own. Yeah, but interesting thing to be noted from this equation is that we can obtain the energy. Yeah, we can calculate the energy of your charge structure if we know the distribution of the electric field intensity E. Yeah, because from this equation, we can further write this as integrations of half epsilon naught of E squared dV. Because we know that D equals to epsilon naught of E field. So when we have D dot E, so it becomes epsilon naught of E dot product with the E field, and we're going to have epsilon naught of E squared. So that's why we have only this equation, yeah, in which the vectors have been changed into a scalar only. Okay, which means that we can find the energy if we know the amount of electric field. Or in other words, it can be said that the energy of your charge structure is determined by the electric field produced by that particular charge structure. Okay, yeah? Now this is what we meant by this equation, in which the energy is basically determined by the electric field distribution. If your electric field is zero, which means that your work is zero. Okay, right. So if we base on the case of your line charge that we have explained just now, which is infinite in length, yeah, so we know that the electric field equation produced, let's say this is your rho L, yeah, we have learned previously in Coulomb's law or in Gauss law that electric field produced, yeah, by this particular charge structure will be E of rho L divided by 2 pi epsilon naught of R, direction of R in volt per meter. So from this equation, we can find the energy produced by this particular charge distribution, in which we can just use W equals to half integrations of epsilon naught and E squared, which is rho L over 2 pi epsilon naught R squared. And then we have a dV, yeah, which is because we are using the cylindrical system of coordinate, going to have r, dr, dphi, dz. Okay, this is how we obtain the energy produced by this particular charge structure. Okay, so we have two formulations to be used here to calculate the energy. You have the options either to use this equation that we have formulated before, which is half integration dq of v, in which dq will be depending on your charge distribution, or alternatively, you can use this equation, half epsilon naught E squared dv integration, in which the difference between these two equations is that for the first equation, you need to know the potential of your charge distribution, yeah. But for the second equation, we just need to know the electric field intensity for the given charge distribution. Okay, so for my case, I personally prefer to use the second equation because we have been very familiar with the E field. We have learned E field from chapter 2 and chapter 3. Okay, so apart from my case, my preferable is to, I much more prefer to use equation number 2, in which to find the energy based on the electric field distributions. Okay, all right. So now we're going to have a look at the examples in which we're going to see how can we calculate the energy by using the equations number 2. Yeah, I'm going to concentrate now only on equation number 2. Yeah, because I mentioned just now, I will just use this equation. I'm not going to use this equation. Yeah, because I don't want to find the potential. Yeah, I just want to find the E field, and from the E field we can straight away find the energy. Yeah. Okay, so this is what I mentioned just now. The energy of the system of charges can be obtained if the E field distribution produced by the charge is known. Yeah. Okay, so let's have a look at this example number 1. Example number 1 is regarding the spherical charge distribution. If we're having a radius of RA of your charge, and we are having the uniform rho v, and the charge is centered at, the spherical structure is centered at the origin. Okay, so if I can sketch the diagram for you, okay, so we have this spherical structure. We have a radius of RA. Yeah, radius of RA. Okay, and the charge distribution is rho v. Yeah, this is a rho v charge. Okay, so the question is find the energy needed to build up the charge system. Yeah, find the energy needed to build up the charge system. Or in other words, find the energy that is produced or that is conserved by this particular charge distribution. Okay, so as I mentioned just now, I want to use this equation number 2, which is W equals to half integrations of D dot E dV, or we can also write this as half integrations of epsilon naught E squared dV, yeah? Okay, E squared of dV. Okay, this is the equation that will be used to calculate the energy of the system. Okay, so in this particular case, in order for us to use this equation, you need to calculate all the electric field intensity produced by your charge structure. Yeah, so you need to calculate all the energy or all the electric field intensity distribution produced by this particular charge structure. So from what we have learned previously, given a spherical charge distribution, you can have two different regions for the electric field. Yeah, two different regions. The first region is R less than RA, yeah, which is inside the sphere. And the second region is R bigger than RA, which is outside the sphere. So you can have two regions that have different electric field intensity. Okay, so we're going to calculate this electric field intensity value because that will be used in calculating the energy. Yeah. Okay, so let us go for the first one, which is for the R less than RA. So that will be based on the Gauss law, yeah, because we are having a spherical structure. So for the first case, that should be your Gaussian surface. That should be your R to indicate this R less than RA region. Okay, so for that, we're going to have the D dot ds. Okay, should be equals to Q enclosed. Okay, right, in which we have learned that the d dot ds is the integration on the Gaussian, enclosed charge is a charge inside the Gaussian. So we can further write this as dr 4 pi r squared equals to the enclosed charge is a charge enclosed by the Gaussian. Yeah, inside the Gaussian. Yeah, the Gaussian is only between 0 to r. Okay, so for that we can write that the enclosed charge will be rho v because of volume charge. Yeah, so we just multiply with 4 over 3 pi r power of 3, which is the volume of charge, sorry, volume of sphere until radius of r only, because that is the radius where the Gaussian surface is said to be bounded. Yeah. Okay then, so the 4 pi, the r can be cancelled out. So left only with the r on the right hand side. So we're going to have then that the dr will be equals to rho v r divided by 3. And as such, we can have d vector as rho v r divided by 3. Or we can have the E field equals to rho v r divided by, this is direction of r, yeah? 3 epsilon naught direction of r in volt per meter unit. Yeah? So that should be our E vector, in which we write this as E1, yeah? As E1 to differentiate between two regions. Yeah, that should be our E1, the first electric field that we have calculated for a region of R less than RA. Okay, for a second case where we have R bigger than RA, so our Gaussian surface should be outside the sphere, outside the sphere, so that should be our Gaussian surface for the second region, R bigger than RA. Okay, that should be our R, yeah? Yeah, to indicate that R now is bigger than the RA radius. Okay, so for that, we're going to have the Gaussian surface, the d dot ds equals to enclosed charge, in which the d dot ds is the integration on the Gaussian. Enclosed charge is the charge inside the Gaussian. Okay, so if we proceed with this calculation, we are going to have the r 4 pi r squared, which is on the Gaussian surface, whereas for the enclosed charge is a charge inside the Gaussian. And if you base on this diagram, we know that inside the Gaussian, the charge will only exist from 0 to RA. Yeah, no charge elsewhere. Yeah, which means that from RA to R, which is the which is the new Gaussian surface radius. Yeah, from RA to R, yeah, from this RA to this R, there is no charge. So for that, your enclosed charge will be rho v 4 over 3 pi RA power of 3. Yeah, so 4 pi can be cancelled out then. Yeah, 4 pi can be cancelled out. This 4 pi can be cancelled out. So we left only with dr equals to rho v, yeah, RA power of 3 divided by 3 of R power of 2. Okay, and in terms of the vector, we can have that the vector D shall be equals to rho V RA, yeah, rho V RA power of 3 divided by 3R squared power direction of R. And afterwards, in terms of the electric field intensity, we label this as D2, yeah, D2. So this is E2, which will be rho V RA power of 3 divided by 3 epsilon naught of R squared direction of R in volt per meter. Okay, so we are now having two electric field intensity. The first one is inside the radius RA, yeah, and the second one is outside the radius of RA as mentioned. Okay, so we have two values of electric field. So these electric field intensity values will be used to calculate the energy. So I put it here that for R less than RA, we are going to have electric field number 1, which will be rho VR of 3 epsilon naught direction of R volt per meter. For R bigger than RA, we're going to have electric field number 2, okay, should be equals to rho V of RA power of 3 divided by 3R power of 2, sorry, 3 epsilon naught, yeah? Epsilon naught R power of 2 direction of R. Okay, So now I need to erase this, this portion because we're going to use it now to calculate the energy. Okay then. So the energy can be calculated, as I mentioned just now, by considering all the regions with the E field intensity value. Okay, so basically you are going to have two regions of electric field in which we can write that the W total shall be equals to W1 plus W2, in which W1, yeah, if I can put it here, is contribution of the electric field for R less than RA, and W2 is a contribution of electric field a region of R bigger than RA, yeah, because we have two values of two regions of electric field, so we need to consider these electric field intensity, both of them, to calculate the total energy. Okay, so let us go for W1 first. So W1, if you base on this equation here, will be half integration of epsilon naught of E1 squared dV. So we're going to have half epsilon naught of epsilon, half integration of epsilon naught. So E1 squared, we just consider the magnitude. So that will give us rho V R divided by 3 epsilon naught squared. Okay, so we are going to have, sorry, this is a dV, yeah? dV will be R squared sine theta dr d theta d phi, because we are dealing with the spherical system of coordinate, yeah? So further on, we're going to have half, yeah? So we can simplify it based on the squared value. So that will be rho V squared divided by 9 epsilon naught, and we're going to have integrations of r power of 4 dr, integration of sine theta d theta, integrations of d phi. Okay, and we can now state the range for these r, theta, and phi. So because we are considering the energy, I mean the full sphere, so phi will be from 0 to 2 pi, theta will be from 0 to pi, and the range of radius r, because our concern will be a region of r less than Ra. So that's why the range of r for the first W1 here is from 0 to Ra, yeah? So if we proceed with this answer, you're going to have half. This will give us 4 pi. So we're going to have 4 pi should be there. Then we have rho V squared over 9 epsilon naught, and that will give us Ra power of 5 divided by 5 in joule unit. Okay, so that should give us the W1, which is the work or the energy in region number 1, which is from 0 to Ra. Okay, if you have any question, you can ask, yeah? Along the way, along my lecture, if you have any question, just ask.
Doctor, may I
Yeah.
know why the limit of integration is 0 to RA?
Okay, because if we base on your electric field 1 just now, what is the range of electric field number 1? The range of E1 will be from 0 to Ra, right? 0 to Ra. Because we have proved just now, based on the equation of electric field, based on the Gauss law, that when we find the electric field, we are using Gauss law. The electric field number 1 is for a region of R less than Ra, which means that this E1 is valid for all value of R as long as the value is less than Ra. Okay, so that is why, because W1 is the energy related to E1, that's why we set a range for the R from 0 to Ra. Is that understood, Rehan?
Okay.
Okay, yeah. So the range of R here will be determined by the E1 region. For instance, is E1 is just between 0 to RA. Yeah, that should be the region of E1. Yeah, that's why we need to set that the range of R should be from 0 to RA. Okay, let's go for the W2. Yeah, hopefully W2 will make it clear for you then, which is a half, again, epsilon naught of E2 squared dV, yeah, because this is dealing with the region of R bigger than RA. Okay, so if you proceed with this, you're going to have half epsilon naught, and the E2 will be equals to, based on this equation here, yeah, this is our E2 here. So in terms of squared value, that will give us rho V squared RA power of 6 divided by epsilon naught squared 9 of R power of 4. That should be our E2 squared, yeah, and dV will be R squared sine theta dr d theta d phi. Okay, so this can be further simplified. We can cancel out few things here. This can be cancelled out. R4 and R2 can be cancelled out. Left is only R squared only. So we're going to have half. I'm taking out all the constant outside. So we're going to have rho V squared RA power of 6 over 9 epsilon naught. Okay, integrations of 1 over R power of 2 dr, integrations of sine theta d theta, integrations of d phi. So since we are dealing still with the spherical structure, we put that d phi is from 0 to 2 pi, theta is from 0 to pi, and now what should be the range of R then? Wei Han, can you please help me on what should be the range of R for this integration number 2?
Zero to R.
Okay, okay, W2 is related to E2, right? So E2 is for which region, Wei Han? E2 is allowable for which region?
R2, RA until R, is it?
RA to infinite. Yeah, because I mentioned here that R is bigger than RA, right? So bigger than RA, which means that the range for the R here shall be from RA and it can goes up to infinite. Okay, is that clear then, Wei Han?
Okay.
Okay, yeah?
Okay.
All right, good.
Understand.
Okay, good. So as mentioned just now, to put the range of R should be determined by the range of electric field that you have calculated earlier. Yeah. So for example, for W1 just now, the E1 is only for region less than RA. So that's why the range of integration is from 0 to RA. For W2, we deal with the E2 in which the value of E field is bigger than RA. So that's why we have the integration from RA to infinite. Yeah. Okay, so I think for this particular integration, you can try to do this on your own because just a simple integration, yeah, and you should obtain the value in joule unit. So afterwards, you can have W2 value. So in order to find the total work that is said to conserve in your charge structure, you need to add W1 and also W2. So that should be your total work or total energy conserved in the structure. Okay, so which means that to find the energy, it is determined by the E field. Determined by the E field, which means that you have to calculate all the electric field intensity produced by that particular charge structure, and afterwards only you can use this equation to find the energy in which you have considered all the regions with the electric field intensity value. Okay, hopefully I make it clear to you on this example. So let's have a look at this example again. Okay, this is an example that we have seen this example basically in previous lecture 8, if I'm not mistaken. But for that particular case, it's calculating the potential. Yeah, but for this particular case, the same questions, but it is to find the energy per unit length in a given structure. Yeah, energy per unit length in a given structure. So if I can resketch this problem, basically we are dealing with a simple coaxial cable which is made up of a central cylindrical conductor of 5 millimeter diameter with an outer conducting sheet which is also a cylindrical coaxial with the central conductors. the internal diameter is 20 millimeters. So if I can sketch the diagram for you, okay, this is your internal conductor, first cable. The diameter is 5 millimeter, so you put the radius only, which is 2.5 millimeter. Then we have the second conductor is outside here. Yeah, that should be your second conductor. Okay, but it's given that the internal diameter, yeah, the internal diameter of the outer sheet. So this is the outer sheet, but the internal diameter is this one, okay, which is equals to 10 milli. Okay, yeah, because the diameter is 20, so the radius is 10 milli lah, yeah. So that should be, that's what meant by the internal diameter, yeah. Sorry, internal radius lah, 10 millimeter. Okay, the space between the two cylinders is filled with air. So this is air only, so we just put it as epsilon naught, the permittivity, yeah, because it's given to be an air. And it mentioned here that the maximum voltage that can be applied between the conductors is 500 volt. Okay, so which means that this potential difference between these conductors, okay, is given to be 500 volt. Okay, so this is similar to what we have discussed last time, yeah? But this time around, we need to find the energy per unit length in a given structure. Yeah, energy per unit length in a given structure. Okay, so how to find the energy per unit length? So as mentioned before, we can use this equation, W half of D dot E dV, in which to find the energy, you need to find the electric field first. Yeah, to find the electric field first. Okay, so last time, in our previous example on this similar structure, we have obtained the electric field intensity value. You can refer back to my videos or my lecture notes before, that electric field intensity E, okay, is given by rho s of 2.5 millimeter divided by epsilon naught of R, direction of R. Yeah, in which this is based on the use of Gauss Law, yeah? Yeah, this is electric field intensity for a region of R between 2.5 milli and 10 millimeter, yeah? So that's your electric field value. And we base on the things, I mean, these equations of electric field is based on the assumption that the charge is only present on the surface of the internal cable. Yeah, so the charge of rho s is only on the surface of the internal cable. So if you can label, that is your charge of positive rho s. And that's why we obtain this equation, yeah? Okay, and you're going to learn in lecture or chapter 5 next week, yeah, starting from this Thursday, that later on, we're going to learn that in conductor, there is no charge. Charge will only exist on the surface of the conductor, yeah, because this is conductor, yeah, given from the question that this is a conductor and the outer side is also a conductor, yeah, it's also a conductor. So there's no charge inside the conductor. Charge will only exist on the surface of your surface of the conductor, yeah. So due to that, we can see that because there is no charge inside the conductor, charge exists only on the surface of your conductor. We can say that for R less than 2.5 millimeter, your electric field will be equals to 0. Yeah, for R less than 2.5 millimeter, electric field will be equal to 0. We can prove this using the Gauss law, and we did this example before, that because there is no charge inside the conductor, yeah, so the Gaussian surface, if you base on the Gauss law, the enclosed charge will be 0. Yeah, so because the enclosed charge is 0, then your electric field will be 0, yeah? Okay, so the same thing is applied for R bigger than 10 millimeter, yeah, which is for this region here, yeah, for this region here that we label here between, yeah, or between 10 millimeter. It can be proved that this region will give us a case whereby the electric field will be 0, because for this particular cable, if we have a rho charge, rho positive s, so positive rho s on this surface, we are going to have a negative rho s on that particular surface. Yeah, negative rho s here on this radius or surface of 10 millimeter. So due to this, there is no electric field outside the radius of 10 millimeter, and we're going to see that electric field for R bigger than 10 will also be 0. So due to this, we can say that for this given structure, the electric field will only exist between 2.5 millimeter and 10 millimeter. Yeah, between 2.5 millimeter and 10 millimeter. Yeah, so that is the region where the electric field is said to be produced or to exist. Yeah. Okay, so we did this example before that the purpose of having this potential difference 500 volt basically is to find the rho s. Yeah, is to find the rho s. So I don't want to proceed with finding the rho s. So you can see the videos on how we find the rho s based on this particular case, in which if we can recall back, what we did is that we just put that the rho s is a rho s naught. Yeah, so we have these terms of rho s obtained from the use of this potential difference, and what I did is that I just put the value to be rho s naught. So similarly here, we just put that the rho s is written to be a rho s naught, yeah, of 2.5 milli divided by epsilon naught of r in the direction of r volt per meter. Yeah, so that is the electric field exists in your given structures. Okay, so to find the energy of the given structure, we just need to consider the E field only between 2.5 and 10 millimeter, because there is no electric field elsewhere. Yeah, less than 2.5 it is 0, bigger than 10 is also 0. So you don't have to consider these two regions here. Our concern is only between R 2.5 millimeter and 10 millimeter. So this is the region of interest for us to calculate your energy, due to the fact that for other regions electric field is 0. Yeah. So for this, we're going to have that W will be equals to half integrations of epsilon naught of E squared dV. Yeah, I have rewrite this equation in terms of E squared dV, and we can have it as half epsilon naught integrations of rho s naught squared 2.5 milli squared divided by epsilon naught squared of r squared. Yeah, so dV will be r dr dphi dz, because we are dealing with the cylindrical systems or coordinate. Okay, so if we proceed with the integration, we're going to have W. We can cancel out this epsilon naught with this epsilon naught. I'm taking out the constant outside, so rho s naught squared is taken out. 2.5 milli is also taken out. Yeah, and we have 2 epsilon naught. Yeah, so I proceed with the integration straight away. We are going to have integrations of dphi, which is from 0 to 2 pi for a full cylinder. Z will just have a integration from 0 to L. Yeah, we just consider the height of your cylinder to be L, a closed structure. And then the R integration will be from 2.5 milli to 10 milli, yeah, to 10 millimeter, because that is the range where electric field is said to exist. Okay. All right. So I hope I made clear to you now. So based on this calculation, yeah, we can see that the W will be equals to, sorry, I have no space to use then. I need to use this space upside here. Yeah, sorry for that. Okay then, so for this particular case, we can say that the energy, yeah, the W will be equals to rho s naught, yeah, squared. We have 2.5 milli squared divided by 2 epsilon naught. We're going to have 2 pi then, yeah. We're going to have L for the height, and we're going to have, sorry, this is 1 over r squared, yeah. Sorry, this is cancelled out, 1 over r, sorry for that, it should be 1 over r, yeah. Yeah, this is r and squared is cancelled out, so 1 over r. So 1 over r integration should give us ln r, and we have 10 over 2.5, that should be ln 4 lah. Yeah, ln 4 for that. Okay, so because the question asks us to find the energy per unit length, so we can bring the L to the left-hand side. So we're going to have W over L shall give us rho s naught squared 2.5 milli squared over 2 epsilon naught times 2 pi times ln of 4. So that should be our energy per unit length, which is in joule per meter unit. Okay, so that should be the answer for this questions. Okay. Any question up to this example? Number 2? No? Okay, if there's no questions, that should be the end of chapter 4. Okay, so let us recap the things that we have learned previously in chapter 4. Number 1, we have learned about the concept of work and energy in electrostatic field, in which we have started with this equation here, W of negative Q integrations of E dot dl. Okay, this is the equation that we have learned previously. And from this concept, we have obtained 2 important hypotheses. The first one is work does not depend on the path. Yeah, does not depend on the path taken. Yeah. And number 2 is that work per unit charge in a closed loop movement will be 0. If we base on the equation, it will be E dot dl equals to 0, which is the second law of Maxwell, which has been produced previously in our lecture. Okay, so that's the important things that we have obtained from the first topic. Then we have learned also about the concept of potential difference and potential absolute potential, in which from the work equation previously, we have W over Q, which equals to potential, will be negative integrations of E dot dl. So potential difference between, let's say, is from A to B, so it should be given by integration from point B to point A, which is the starting point to the end point. And that will give us the potential difference between the 2 points and also return to be VA minus VB. Yeah. So that is your potential difference produced by the concept of work from the first topic. And absolute potential is when your B is at infinite, and this is the case where we can say that when B is at infinite, you can have the VA, and the VA is your absolute potential value. Yeah. Okay, that should be number 2. Number 3 is about the concept of potential gradient, yeah, which enable us to find the electric field intensity. E equals to negative grad of V. So we have learned that the gradient will be depending on your coordinate system. Okay, and finally, we have just covered this topic, is calculation of the energy in the electric charge system, in which we have the equation of half integrations of D dot E dV. Yeah, and we did 2 examples related to this calculation of the stored energy in the charge structure. Okay, so that's the end of chapter 4. So this Thursday, this Thursday we're going to start a lectures on chapter 5, in which we're going to start the topics of current and the topics of conductors and conductivity. Yeah, so 2 topics will be covered in our lecture this Thursday. Okay, so we still have time. So let us have a look at this example. This is an example related to the concept of potential and also use some ideas on Gauss Law to find the electric field intensity. This example, we are given a case of a current carrying electric cable, which is shown in this figure question 1a. Yeah? So your cable is located here. Yeah, this is your cable. Okay, your cable is here. The cross section of the cable is given by question 1b. So this is the cross section of the cable. It consists of 2 conductors basically, 20 cm radius, rho v is 0, relative permittivity is 1. Okay, for the outside conductor, outside cable, radius is 50 cm, and the rho v inside that particular region is 12 over R coulombs per meter cube, yeah, which is a volume charge, and this is relative permittivity, which is 3.2. So we're going to learn this in detail in chapter 5 later on. Okay, never mind. So the question is obtain the electric field intensity for all region, which is inside and outside the cable. So that's what meant by this question. Okay, so we need to use the Gauss law to find the electric field intensity in these problems, because we are not given any conditions on the length of this electric cable. So we assume that the length is infinite, it's very, very long. So we can straight away use the Gauss law to find the electric intensity. So if based on this particular region, these particular conductors, we have three regions to be considered. Yeah, the first region is R less than 0. Sorry, not, my apologies, not R less than 0. It's R less than 20 cm. Yeah, R less than 20 centimeter, which is a region in the gray color here. Yeah, in the gray color, in which the rho v is 0. Okay, and if you base on the Gauss law, yeah, if you base on the Gauss law, if I can sketch the Gauss law for this particular region, so that should be our Gauss law. Yeah, the Gauss law then, yeah, we can see that for this particular region, the d dot ds of Q enclosed, we can see that there is no charge inside this Gaussian surface. Yeah, no charge inside the Gaussian surface, because why? Because the rho v is 0 inside this gray colored structure. So due to this, knowing that the Q enclosed is 0, so we can straightaway see that the D will also be 0. And as such, the electric field intensity E1 will be 0 also. Okay, so that is the first electric field that has been obtained for a region of R less than 20 centimeter. Yeah. Okay, next region is R between 20 centimeter and 50 centimeter, which is between this region, between 20 and 50 centimeter, in which for this particular region, the rho v or the charge distribution is given by 12 over R coulombs per meter cube. Okay, so we sketch the Gaussian surface for this particular structure. Yeah, so basically the Gaussian surface should be a cylinder. Yeah, so but I just sketch it, the cross section of it. Yeah, but to make it clear for you, so that should be the Gaussian surface. And the same things applied, yeah, for the first Gaussian surface just now, which is also in a cylindrical structure basically. Yeah. Okay, so for this case, for the second region, yeah, that should be R, yeah, Gaussian surface of R radius. So we have d dot ds equals to enclosed charge. So we have for left hand side, it should be dr 2 pi rl. If we put that the length of your Gaussian is L, yeah. So we have 2 pi rl, and the enclosed charge will be integrations of rho v, which is 12 over R, and the dV will be R dr dv dz. Okay, that should be our dV, yeah. So if I can write here, so enclosed charge will be integrations of rho v dV. Rho v is 12 over R for that region, and the dV will be R dr dv and dz. Yeah, so R can be cancelled out. So we have a dr shall be 12 integrations of dr, integrations of dv, integrations of dz divided by 2 pi rl. So R will be from 0 to R, yeah, because that should be our Gaussian surface. And phi 0 to 2 pi, while Z we put it from 0 to L. Yeah? So end up we can have it as 12 R squared divided by 2 for the R integration. Sorry, there's no R. Sorry, my mistake there. Sorry for that. Okay, sorry, it's my mistake. There should be R only. Yeah, there should be R only here. So we have R. That should give us 2 pi, and that should give us L divided by 2 pi RL. So this can be cancelled out altogether. So we only have 12, which means that the vector D will be 12 direction of R coulombs meter squared, or we can just have E2 should be 12 direction of R volt per meter. Okay, so we have this electric field number 2. So I can put it here. So R less than 20, it should be E1 equal to 0. For R between 20 cm to 50 cm, so your E field E2 will be equals to 12 of R in a vector volt per meter. Okay, so we're now going to proceed with the third electric field. Yeah, the electric field, which is for the region of R bigger than 50 cm. So I need to use this space here. I need to erase this space. Sorry for that. Yeah. Okay then. So we can now change this range for the integration for this E field, which will be R bigger than 50 centimeter outside the sphere, sorry, outside the cylinder. So that should be given by the cylinder here. That should be a Gaussian surface, the new Gaussian surface. Yeah. Okay, that should be a Gaussian surface then for the third region, and that should be the R. Yeah, that should be your R to indicate the third region bigger than 50 cm. Okay, so for this we are going to have the R 2 pi RL. Yeah, which is R is for R bigger than 50 cm. Yeah, and then the enclosed charge will be the charge inside the Gaussian. Yeah, inside the Gaussian. Sorry, I think I make a mistake. Yeah, I think I made a mistake for this case just now. Sorry for that. I think I make a mistake for that particular case. We have a, sorry. The mistake is very obvious. I'm very sorry, my mistake. Sorry. Okay, for the second case, which is R between 20 cm and 50 cm, basically you're going to have dr 2 pi RL, enclosed charge is integration of 12 over R, dr, dphi, dz. Yeah, and then we're going to have dr close to 12, so this is R, yeah? 12 of integrations of dr, okay, integrations of dr, integrations of dphi, integrations of dz, yeah? This is from 0 to L, this is from 0 to 2 pi, and basically for the R, it should be from 20 cm to 50 cm. Sorry, I might make a mistake just now. Not from 0 to R, yeah? It's from 20 cm to 50 cm because this is the region where we have the charge. So that's why we need to put that range of R integration should be from 0 to 0.2 meters to 0.5 meters. Not 0.5. Again, I make a mistake. It's from R, yeah? It should be to R then. To R, yeah? 0.2 to R. Because our Gaussian is from 0 to R. So the range of integration which consists the volume charge should be from 0.2 to R only. Okay? And then it divided by 2 pi R of L. So if you proceed further, we're going to have 12 R, which is from 0.2, okay, 0.2 to R. Then we have 2 pi, we have L divided by 2 pi RL. Okay, so this can be cancelled out, 2 pi, L can also be cancelled out. So we only have then as a 12, yeah, R minus 0.2 divided by R. Okay, so that should be your dr. Okay, I hope I make it clear now. Sorry for my mistake just now. Yeah, it is my mistake. Is that clear on this? Any question for the second region from 20 to 50 cm? Is there any question for that?
Me no, Doctor.
No, yeah? Okay, if no question, let's proceed then. So basically from this dr, we can find the vector of d straight away. I put it here that the vector d, if you can write it, the vector d for that region will be 12 of r minus 2 or over r in the direction of r, and as such you can see that the electric field intensity number 2 shall be equals to 12 of r minus 2 is 0.2, r minus 0.2 divided by r, epsilon of r in the direction of r. So that should be our electric field for region number 2, yeah? Okay, so, right, so hopefully it's clear, yeah? Yeah? I make a mistake with this. Sorry for that. Okay, so let us proceed with the third region, which is for r bigger than 0.5 meter or 50 cm. Okay, okay, so for this particular case, we have Okay, this is for R bigger than 50 cm, yeah? R bigger than 50 cm. Okay, so that our Gaussian surface is here with the radius of R. So we can see that this will be written as a dr 2 pi RL, whereas for the enclosed charge, it will be integrations of 12 over R. Rho V will be R dr dv dz. This one can be cancelled out still. Okay, so we're going to have 12 integrations of dr, integrations of dv, integrations of dz. Yeah, that should be dr 2 pi RL. Yeah. And from here, dr will be 12. So what should be the range of integration now for your dr? So that should be the charge inside the Gaussian. Yeah. So charge inside the Gaussian for the R range will be from 0.2 to 0.5 meters. So you put the R should be from 0.2 to 0.5. Phi will be 2 pi straight away, and Z we just put as L, yeah, because we put the range of phi from 0 to 2 pi. Z is from 0 to L, so we have this equation, and that will be divided by 2 pi R of L. Okay, so 2 pi can be cancelled out, L can be cancelled out, so you only have then the dr shall be equals to 12 multiplied with 0.3, yeah, divided by R then, yeah, because when we integrate this value, yeah, so that will give us 0.3, yeah, 0.5 minus 0.2 will be 0.3, and that will be divided by R, and as such, that will be 3.6, yeah, 3.6 divided by R, and you're going to have that the vector of D will be 3.6 divided by R, direction of R, yeah, coulombs meter squared. So as such, we can say that for R bigger than 0.5, or just we put it as 50 centimeters, the E field region number 3 will be 3.6 divided by R, the epsilon naught of R, direction of R, volt per meter. Yeah, so that should be our electric field for region number 3, which is for a bigger than 50 cm. Okay, so we have calculated successfully 3 electric field values. The first one is for R less than 20, which is 0, E1 is 0. For R between 20 and 50 cm, in which I made a mistake earlier, basically it should be 12, and multiply with R minus 0.2 over epsilon naught of R. Okay, if you assume that, yeah, in this case, I assume that this is epsilon naught, yeah, equals to 1 also. Yeah, so we just assume that inside this region, the space is permittivity is a free space, yeah, so which means that we just have epsilon naught. We just ignore the 3.2 permittivity, yeah, because we are yet to learn about these topics of relative permittivity. The same things applied for the E3. We just assume that it's just a free space region, so that should be the value of electric field intensity for the region of R bigger than 50 centimeter, yeah. Okay, so that is your electric field, in which we have used the Gauss law to find this electric field intensity for these 3 regions. Yeah. Okay, now we are going to continue the questions in which, for this particular questions, which is part number 2, the radius distance of student A who is working under the cable is estimated to be 5 meters from the cable, while radius distance of student B is estimated to be 7 meters from the cable. Obtain the potential difference between the students. Okay, so we have student A and B here. Student A is having a 5 meters, we call that a distance, and student B is having a distance of 7 meters from the cable. So the question is to find the potential difference between the students. Yeah, so what should be the potential difference between the students in this particular case? Okay, so in this particular case, in order for us to find the potential difference, yeah, we can use the equations of V equals to negative integrations of E dot dl. Yeah, E dot dl. Okay, so if I can resketch the problem just now, that is your cable, yeah? That's your cable. So the A is here, which is having a distance of 5 meters from the cable. So the B is here, which is having a distance of 7 meters from the cable. Yeah, 7 meters from the cable. The question is find the VAB, which is a potential difference between student A and student B. Okay, so before we can start with finding the potential of V here, we need to actually understand, or we need to actually identify what is the electric field intensity E that shall be used here. Okay, so previously we have three electric field value, right? The first one is for R less than 20. Then we have R between 20 and 50. And then we have R bigger than 50. So in this particular case, which electric field terms that shall be used? So we have R less than 20, which is E1 equals to 0. R between 20 and 50, we have E2, which is having the equation for that. And then we have R bigger than 50. We have E3 equals to 3.6, 3.6 divided by epsilon naught of R direction of R, volt per meter. So in your opinion, which electric field intensity that shall be used in this equation of E dot dl to find the potential difference between A and B? Can I ask Chai Bing Cheng? Chai Bing Cheng, are you in my class now?
Yes, doctor.
Okay, can you please identify which electric field intensity shall be used to calculate the potential difference here?
I'm not sure, doctor.
You're not sure.
Yeah.
Okay. Can I ask Tae Jing Yi? Tae Jing Yi, are you in my class now?
Yes, doctor.
Okay, can you please identify which electric field should be used to calculate the potential difference in this case?
Is it the second one, 20, between 20 and 50?
Okay, it should be the third one, Jing Yi.
Okay.
The third one, yeah, because your structure is located outside the cable. Yeah, located outside the cable. So because the structure is located outside the cable, you have to consider electric field for a region which is outside the cable. In this case, is the E3. Yeah, so we have proved just now that the E3 is the electric field outside the cable, which is having a radius of bigger than 50 centimeters. Yeah. Okay, thank you, Jingyi, for your response. So hopefully you understand, yeah, why we choose R bigger than 50 cm. Thank you very much. Okay, so now we just set a potential V negative integration. So the E will be the E3, which is a 3.6 over epsilon of R, direction of R, and your dl should be dr direction of R. So your integration may be from point B to point A, yeah, because you need to find potential difference between A and B, right? And we are going to have potential difference now to be 3.6, yeah, over epsilon naught, yeah, integrations of 1 over R dr from A to B, yeah, because I've changed the negative sign. Yeah, I've canceled the negative sign, so the integration will be then reversed from A to B then. So A to B basically is the distance from the cable, and then we're going to have a 3.6 over epsilon naught integration from A, which is 5, and B, which is 7, 1 over R dr, and end up we're going to have potential difference should be 3.6 over epsilon naught of ln 7 divided by 5 in both units. Okay, so that should be the VAB, which is a potential difference between the point of A and the point of B. Okay, so if you base on this, it can be stated that, yeah, you can see that the potential difference is just depending on the distance of the point from the cable, and it does not depend on the distance between the points. Am I right? Yeah, let's say we have a length of L between the 2 points A and B. So is it considered in this calculation of potential difference? No, right? Yeah, potential difference is just depending on the R. Yeah, depending on the R, because the electrical intensity that we have is depending only on the R, on the radius of these, on the point distance from the cable. Yeah, so if you have A, for instance, yeah, if you have the cable like this, the point of A is here, the point of B is here. Okay, this is a 5 meter, this is 7 meters, for instance. If I put B, let's say initially it's a 10 meter distance between the 2 points. And if I put B further away, let's say at 20 meter distance, the same point, B, 7 meters distance also from the cable, we can say that potential difference VAB for the first case equals to VAB for the second case, because it does not matter the distance between the 2 points. Yeah, we just matter about the distance of the point from the cable. Okay then, so this is the things that you have to understand, the concept that you need to understand from the potential difference topic. Yeah. Okay then, I think that is all for